Hello, my name is Gemma. I'll be your moderator for this session. Just a quick reminder that we will have time for a brief live Q&A after the presentation, so please be sure to use the Ask the Speaker tab to ask questions and engage with your fellow attendees. And now it's time to welcome Manish and Vinitha from Apple to the stage for their session, Apache Iceberg powering Open Data Lakehouse at scale. Over to you.
Thanks, Gemma. Hi, everyone. I'm Vinitha, and I lead infrastructure efforts focused on interactive analytics at scale. Over the last few years, I worked with teams to modernize our data platform using open technologies like Iceberg and Trino. Manish?
Yeah, thanks, Vinitha. Yeah, this is Manish here. I'm also working on the infrastructure side in Apple from few years, and predominantly worked on the query engine side and Iceberg for some of our large scale initiatives. Thank you.
Thanks. So today we'll share our journey to building an open lakehouse along with key optimizations and learnings that helped us scale it effectively. So here's a quick overview of what we'll cover today. We'll discuss why we moved to an open lakehouse, the architecture and components that power it, the challenges we faced at scale, and how we address these challenges and some of the key best practices. Let's start with the motivation behind the shift to an open lakehouse. Traditionally, analytics platforms relied on two very different architectures, data lakes and data warehouses. Data lakes offered flexibility. They could store all kinds of raw data at low cost, but they often became messy and ungoverned with inconsistent performance. As they grew, scaling became a challenge, especially when more users and workloads were added. Data warehouses, on the other hand, delivered structured and fast queries, but they were expensive, rigid, and difficult to scale for large dynamic datasets. And you were typically logged into a single vendor's ecosystem, which limited flexibility and long-term costs became unpredictable. So the open lakehouse model aims to give us the best of both. It lets us keep data in open formats on cloud storage, but adds the performance and governance you'd expect from a warehouse. It solves the scaling issues of legacy systems and supports fast and interactive queries. It's modular, vendor neutral, and built on open standards. You get flexibility without sacrificing control and performance without lock-in. Now let's look at what the architecture actually looks like in practice. It's modular, scalable, and open at every layer from ingestion to consumption. At the bottom, there's the ingestion layer. The data comes in through batch pipelines and near real-time sources. It includes a mix of structured and semi-structured datasets, semi-structured formats, depending on the use case. That data then lands in object storage and is managed using table formats such as Apache Iceberg. And Iceberg gives us features like snapshot isolation, schema evolution, and hidden partitioning. And it also supports atomic operations like inserts, updates, and deletes, bringing warehouse-like reliability to open storage. Above that is the catalog layer. While Hive Metastore is still commonly used, many modern deployments are adopting the Iceberg REST catalog, a stateless scalable alternate that integrates easily with query engines like Trino and Spark. For governance, many platforms use tools like Apache Ranger, which provide centralized policy management, access controls, and auditing. And in some cases, Open Policy Agent, OPA, is used as a policy engine to support more customized access control scenarios. Next, we have the processing layer, which handles large-scale data transformation and orchestration. This includes everything from ETL jobs to lightweight data prep and enrichment before the data actually reaches the consumption layer. And at the top is the consumption layer, which is typically ad hoc analytics, interactive queries, business intelligence, and all of this, which is powered by query engines like Trino, which gives us fast interactive SQL access to Iceberg table. So altogether, the stack gives us an open, governed, and high-performance analytics platform designed to scale independently across compute, storage, and metadata. So of course, building the architecture is just the start, and operating at scale brings a different set of challenges. And these are some of the things that we had to solve to make the system reliable and fast in production. First, there is data and metadata growth. So as more snapshots are created and more small files accumulate, both data and metadata grow in size. And over time, this adds overhead to query planning and slows down even simple operations like scans. Second, we deal with mixed workloads. So the platform supports everything from lightweight interactive queries to heavy batch ETL pipelines. And these workloads hit the systems in different ways. Some are short and bursty, and others are long running and compute intensive. So balancing them consistently is difficult, especially as usage grows across the teams. Third, we see performance variability. So what was fast last week might be slow today, and factors like data layout, file sizes, or concurrency can shift silently, and performance starts to degrade unless someone is actively watching. And finally, we hit storage pressure, especially during high concurrency writes. We see things like write skew, IO saturation, and throttling down by the object stores. In the rest of the talk, we'll look at some of the optimizations to address these challenges. So as data volume and usage grows, keeping the lakehouse fast and efficient requires active optimization, especially around layouts and metadata. One of the things we focus on is data and metadata compaction. Over time, streaming jobs and small batch writes create lots of small files, and these increase query planning overhead and hurt performance. Compaction jobs help merge those into larger and more efficient files. Similarly, Iceberg metadata can become bloated if snapshots and manifests are left unmanaged. We routinely compact metadata and clean up unused files to keep table metadata lightweight and efficient. We also expire old snapshots regularly, while Iceberg's snapshot-based architecture enables time travel and rollback. Retaining too many snapshots adds metadata overhead, and expiring them keeps the system lean and planning times consistent. Another critical area is table layouts. Poor partition choices lead to excessive file scanning and unpredictable performance. So we evaluate partition specs based on how the data is queried and how it grows over time. In addition to partitioning, we often apply sort order optimizations to improve data locality, especially for common filter conditions. This helps with efficient reads, compaction, and downstream transformations. So while layout and compaction are essential, they are not enough on their own, especially when workloads and usage patterns are constantly shifting. That's where the feedback loop comes in. We capture detailed information from every SQL query, like what data it accessed, how long it ran, and how many files it scanned, CPU memory usage, and so on. We correlate that with cluster-level metrics like CPU pressure, memory usage, and I/O contention, giving us a full picture of both what's running and how it's impacting the system. From there, we can start to spot patterns. Maybe a certain table is constantly scanned with filters that don't align with its partition layout, or a group of jobs is consistently causing CPU spikes during certain windows. With that insight, we generate targeted recommendations, such as to adjust partitioning, schedule compaction, tuning job concurrency, or scaling resources during peak periods. Over time, this feedback loop allows the platform to move from manual tuning to adaptive optimization, and where the system learns from real workloads and gets better at serving them. Next, Manish will do a deep dive on the best practices for reads and writes. Manish, over to you.
Yeah, thanks, Vinitha. And hello all. Yeah, again, thanks, Vinitha, for sharing the Open Lakehouse reference architecture and like also sharing what could be some of the challenges and highlight the importance of optimization and query events, which are very critical for large lakehouse deployment. In the second part of the presentation, I'll go through in depth for some of the best practices which we observed till now, which are read and write related, and then ends up with the key takeaway. So let's start with the uh, read best practices, and yeah, cool. So, and while doing that, I'll also try to mention some of the work like what we have done in open source world and what we are doing right now in these two categories, and also some of the open source features which we believe and which we observe like are important for the large lakehouse deployment. So yeah, in the best practices for read, as we see there are few features which we mention is like NDV stats, which are stored in the puffin file index, puffin file format, then aggregate pushdown, how to use the metadata of Iceberg to answer some of the queries. Then we'll talk about the metadata and data caching, materialized views, which can pre-compute the results, and then some of the thread pooling which we observed, which can become critical for large-scale tables and the large-scale deployment. So let's start with NDV stats, please. Thank you. So as you see in the diagram, first we are trying to show like couple of different engines and how the NDV stats is kind of tied together in the Open Lakehouse world. And before we get into that, like NDV is a number of distinct values, just to kind of give a proper name to that. And distinct values are basically critical for estimating cardinality and selectivity of filters and joins. So it's very crucial for engines like Trino and Spark while reading the data and querying the large tables. And if I just summarize, like try to see what's the exact value of NDV in the overall flow, is that NDV can leads to better join reordering, and that leads to less shuffle, and that makes our queries faster. So this is how like I see NDVs are important. Now going back to the diagram, and then we'll see a little bit more detail about NDV and some of the observation what we have in TPCDS. So in this diagram, we are trying to show like uh, typically NDVs can be generated in two ways. One way is like through Trino, we can run commands like analyze stats on the table, and recently it is being added to Iceberg as well. In this diagram, we are just giving a reference architecture that okay, we are using Trino to generate the stats using analyze. So that's the top down flow. You see the top green arrow that is running the analyze stats command on Trino, and Trino is generating the analyze stats in the puffin file format. Trino can also generate stats or update stats using configuration extended config while writing and updating the data as well. So in that way, when somebody is writing data from Trino, at that time also the stats can be updated, though we know I think that's not the typical case because Trino is not used a lot for the writing path. So this is how like we see the NDV stats can be generated or are supposed to be generated. Now the advantage we saw, like it can reduce which we discussed, it can reduce the shuffle. So when it reduces the shuffle, now if we go in a little bit detail, it is basically it is helping us to do file pruning and skipping. Basically then Trino to identify the skip irrelevant files during the query execution, and which can again lead to reducing the amount of data read and process. So this is the underlying like advantage of keeping NDVs. Now NDVs are also like right now stored, stats are at the column level. So when I'm doing analyze a table, I can also analyze on all the columns by default or reduce to a certain columns. Now, why it is important is that because NDVs or stats can also become heavy if my table is pretty wide and also it is very heavy. So we also have to be careful about like how much stats we want to write, which can impact my write path, and it can also impact my read path, because it's the same coordinator has to process the query on that big table where there are a lot of stats, and the tables which are like less stats. So it can have a regression on the other queries as well. So that is also we started observing, and like we have to be careful. That's what we can suggest. And we are also discussing like how we can make it configurable on the Trino side, like uh, by default, like if we can generate stats only for certain columns which I know which are going to be used in predicate or in the joins, so that I'm not generating unnecessary stats. Lastly, like the NDV stats, without NDV stats and with NDV stats, the queries can be TP-CDS queries. The can be 5 to 10x faster. So, and some queries can be much more faster, again based on the context of the query. Next slide, please. Next topic which we want to discuss is aggregate pushdown. So we saw in the previous slide about the advantage of NDV stats. Now, aggregate pushdown is also related to stats. Here we are talking about min, max, and count. We have not integrated it with NDV stats yet. But the overall idea is like if we can avoid generating the splits and processing the actual Parquet or ORC file for answering some of the aggregate queries, and if we can leverage the Iceberg metadata which is available and which is automatically generated whenever the data is ingested or updated, that can give us great value for certain type of queries. So if we see in the diagram, the left side of the diagram shows the optimal path, and the right side of the workflow shows the regular path. So in the optimal path, what we are saying is that because the data file the Iceberg data file already consists these stats, during the planning time itself, based on my filters or predicates, and which I also can push down those filters in Iceberg, and I will find the data files which are relevant for me. From that, I can pick those stats and calculate the aggregates which user is looking for certain queries, and get those numbers ready, and then formulate the results. Now, these queries won't be as complex, won't be the complex queries, but these queries, what we observed is like frequently running queries, which users are doing it to find some of the stats and counts for either for dashboards or for analysis. And these are like a lot of queries which people are querying just to calculate those stats. So this, in our observation, like in some of the queries, can literally give us 10 to 15x of boost in terms of CPU saving, as well as the latencies, especially when somebody is trying to get min or max on non-partition columns. So that's where we see a great advantage of this. And the other advantage what we see in using this feature is that if somebody is trying to get the using the partition metadata table in Trino, it is executed on Iceberg, on the coordinator, as well as it is not optimized. It has to read through all the partition stats and then give the answer. Instead of that, some of those queries can also be answered through the aggregate pushdown feature, and it can save a lot of resources of the coordinator and cluster, and we can further reduce the cluster size. Next slide, please. Now, as we saw the stats, and then how we can use the stats for NDV and aggregate pushdown, the next one which we want to discuss is the caching. And especially the data caching feature which is there in Trino with the Iceberg connector. And this is being added in Trino, which is based on the Elixir library. So Elixir is another software which people can also use it as a separate distributed cluster. But in Trino, what recently being added is it is integrated as another file system. So it is abstracted from the user, and the files are being written on the local disk of the worker, and that is also transparent from the user. So Elixir is being integrated. We have also worked with the open source community to bring this feature, and now advantage of this feature will be based on certain queries. Like if we are having a repeated data set, if the data set I'm going to use repeatedly from multiple queries, then definitely the caching will help. Um, Also, like the caching in Trino is also integrated at coordinator level, and that also can give a huge boost, and that is for the metadata of the iceberg. So because sometimes, as we have discussed in other places as well, if my iceberg table metadata is becoming huge, and which is happening, and so this feature can also give us like release the pressure on the storage path and the planning time, and can make those queries faster because the metadata is being cached on the coordinator. Um, um, yeah, so that's about the data caching. The last observation what we had is we see like the TPCDS queries can be scaled or can get benefit up to 30% improvement based on Elixir local caching, which is there with Trino. Next slide, please. Um, Yeah, so this is now let's discuss about the materialized view feature, which we know can help in certain cases. It has certain constraints as well. Having said that, so materialized view is basically is a pre-computed results, which is actually stored on disk and not being read from the base table from which I have created the view, which is typically happen in normal views. But in this case, what I want is I don't want to pre-compute the results every time. So that's when we create materialized view. Now in Trino, right now, Trino has a native materialized view feature on Iceberg tables. And there is an incremental refresh feature as well, which we also worked with open source community to bring it in. But incremental refresh feature is not covering all the aspects right now of the queries, and it needs more work to support like nested queries and then complex joins. Right now, it is supporting a certain set of features, which we feel is again like is good enough for certain use cases, and definitely uh, it's a good feature to understand and leverage to see like where it can fit in your architecture. Having said that, like the third point what we put is like the base iceberg table. So basically the iceberg table which is created as a result of the materialized view is abstracted, and it is not like it's not like a normal table or when we create as an iceberg table. uh, and then the last point is more about the performance benefit. So I'll go a little bit. I think it needs more talking points than just on the slide. So on the performance or improve query performance, one is, as we discussed, it is pre-computed results. It can save cost, and when we are talking, like, it can literally save cost, because if my queries are complex, I mean complex in terms of the data size, then if I don't need to pre-compute every time, if my use case is like that, it can really make a difference. And we can use that resources on Trino for other queries, because Trino we typically run for multi-tenant environment, and it is not easy to slice and dice for different use cases. So it can really give us benefit. The other advantage what I see is like it is non-performance, but I see a great value in that is the simplify query design. In that case, like how I envision is like end user, which is like data engineer or business analyst, when they are using the system for querying, if we provided materialized view or in that those cases, I'm also abstracting the complexity of the query from those users. So maybe they don't need to know about the overall complex data model, which I have in my backend data warehouse or lakehouse. So that also an advantage what I see. Lastly, like the issues I've already talked about, issues in the sense that there are constraints of incremental refresh. The other constraint is more of a interoperability of materialized view across the engines, and there are discussions happening in open source community about that as well. Like I believe and we are hoping like on the line of iceberg views, we can work with the community to bring to a fruition like for materialized view as well, and that can help the whole community a lot actually. That's what we feel. Next slide please. Thread pool sizing, which is like uh, in thread pool sizing, basically there are we can tune certain thread pools when we are using Trino and Iceberg. That is what our observation. And two critical one is Iceberg worker number of threads, which is basically it is used by Iceberg library. It is per JVM, and it is used for initial planning and to control the parallelism while processing the manifest files. Uh, so that is kind of the role of this thread pool. And the second is Iceberg split manager number of threads, which Trino uses to process the Iceberg metadata to generate the split. So that is a separate thread pool, and that is also being added not very recently, but it was not there from origin, like in Trino. But now it's a separate thread pool. Both are the default size of both the thread pools is 2 times number of codes. Now, when it becomes like not little, but important to understand like how it can impact my queries, is that if I going back to certain use cases where suppose we have tables which has larger metadata and my cluster is multi-tenant, so I'm running like hundreds of queries at the same time. Now what happens is like because my Iceberg number of threads is suppose I set as default, which is suppose 2 times 96 if I have 96 codes, then those many threads will be available to process the manifest files, and it controls that task list. Now, when that happens, then it also correlates with how many files or connections I'm opening on S3. And when I'm opening on S3, there is a limited S3 connection pool which I have on the Trino coordinator. So what it can correlate to, if I have higher number of threads on Iceberg number of thread pool size, I have bigger metadata, big tables, concurrent queries, then I can exhaust the S3 connection pool. So then I have to like write on paper the numbers and kind of figure out like what's the optimal number for this thread pool size and the S3 connection. Otherwise, it will deteriorate the experience and queries are failing and people are retrying. So that's like an important lesson what we can share. There are some open source work and discussions also which we did on the Iceberg side as well, to where we understand the parallel iteratable model of Iceberg query planning, and then we also add a patch to mitigate one of the risk where it can go to a potentially deadlock when in a high concurrency environment. Next slide, please. Thanks. Now the read part was pretty heavy, like because that's like more of an observation and more of the use cases of Trino is read heavy. But there are certain observations and best practices what we understand for writes as well, because still there are production use cases or cases where people are using write or ETLs through Trino. So first is the how we can rate limit the writes. And when I say rate limiting writes, this whole context of all these 3 points will be related to S3, just to set the context. So when we are using S3, as we know, there will be a limited number of reads and writes per second. What S3 can provide us per S3 partition or S3 key. We'll discuss a little bit more in detail, but at a high level, I can be throttled by S3 for writing data or reading data. So when I'm writing from Trino, I can use some configs like write max task, which can help to create a little bit of back pressure on the Trino side itself, instead of like writing whatever is comes in the query ETL. And so that it again, we have to play around with that number and figure out like what's the optimal for my use case. But that's very handy in those situations. Other thing what we have observed is the write max task was honored for non-partition tables, but it was not honored for the partition tables. So that's where also we recently worked with the open source community, and the partition based support should also be there now for those tables, and where we can use the write max task. Next point is partition data and entropy. And this is to kind of go a little bit more detail into that. Let's quickly see how S3 storage treats the paths basically, and that will leads us to these two points as well. So S3 storage based, like my understanding is S3 storage treats prefixes as the key to identify the value and content, like the actual file or whatever content I have which I'm trying to read. And if the same key is used to read and write a lot, basically that can become like a hot key or hot partition for for S3. And S3 has, if I'm not mistaken, like I think 3,500 writes. That's the limit, and 4,500 for reads per S3 partition or key. So if I'm keep writing and reading data from the same partition key, then I'm ending up getting a lot of again the throttling, which can deter my queries. So to circumvent that, I think there could be two approaches. One, we know that we can have the partition data, which is required for in general for Iceberg as well for query and performance, but it will also help in S3 prefixing and distributing the keys within S3 metadata, which S3 maintains to give us the answer when we are accessing data or file from a particular path. The second one is entropy. And entropy is also a feature which is added in Iceberg, and which is driven by the property write object storage enabled, and which is also supported by Trino. And in a nutshell, like what this feature does is like it will add the prefix to my file path, a hash generated prefix to my file path, so that now there is a distribution of that path in S3 metadata as well, so that I'm scaling out my read and write throttling, which I was bound to one partition or one key. So that's and it's very powerful. And I believe in Iceberg, when it was started, that feature, it was hex code based entropy. Then in 1.5, I think it is base 64. And then I think in the recent versions, it has further improved based on, I think, what we have learned from this. I think it is now based encoding, and there are 20 characters, and then each 20 characters are divided into 3 directories, which can again further help to other operations. Instead of hitting one directory, there are like 3 directories in the path. So yeah, but it is really helpful, and I think if anybody is like using Iceberg on S3 at little like medium scale or large scale, like this should be enabled, and this should help. The last one which we wanted to talk about is dedicated connection pool planning. This is more of a Yeah, so this is basically correlated to the thread pooling. So the same iceberg number of thread pool is used for planning as we discussed. And what we observed is it is also used when we are deleting the data. So what happens like if you are deleting like large number of like big tables, and then if the same thread pool is being used, then it can exhaust uh, the threads, and it can be like waiting. It is waiting for IO on S3 or whatever storage layer you're using. Then my regular queries are also starving. So this is our observation. I think this is like more like we are also discussing right now with the open source community. Like, is there anything else we can do for it? But yeah, this is like a note what we had. Thank you. Next slide, please. Um, yeah, I think this, I promise this is the last slide. So in key takeaways, what we are trying to say is like maybe just like to recap what Vinitha mentioned, couple of very important points. Open Lakehouse is the way to go, and in that there are multiple layers, but the layers like which we have kind of worked on and have a little bit of observation, that is Trino and Iceberg. So we say Trino and Iceberg are the critical component when we are laying out the Open Lakehouse architecture. Then the second point is about intelligent table optimization, going back to table management, which is very critical. The forward-looking thing in table management would be to make it more adaptive instead of based on static configuration, so that it is kind of hands-free from the user perspective, and it can also leverage the stats automatically to figure out what could be my say write file size and metadata size as well. Then stats and indexes. Stats, we again discuss NDVs. We can see, and we can like the stats has to be there, and then there is a need for automation and framework to keep generating the stats. And also one more interesting thing correlating to what Vinitha said about the query event and correlating the results. We also feel like we need more information about the stats and correlating that with the queries there. And for indexes, like there is a discussion in open source like about the secondary indexes, and we are looking forward to it. And then the resource forecasting and scale out reads and writes. Resource forecasting is about the query events and how we can intelligently correlate with the resource metrics and forecast the requirement. Scale out read and writes is more about entropy. That's the like key takeaway for us as well in last couple of in the write path and read path. And the last is modern catalogs, which is Vinitha mentioned about the catalog, importance of the catalog. We have not discussed a lot in this presentation, but it is the Iceberg REST catalog is the catalog to go. Yeah, I think I'm done with my content, and then thanks a lot. Thank you for listening, and yeah.
That's great. Thank you so much for that. That was really fascinating. We've got about 6 minutes left, so I think we've got time for maybe one, possibly two questions. I'll go for the one with the most votes first. Do you use Z order when compacting Iceberg tables? If so, when to use it instead of regular ordering?
Vinitha, you want to?
Yeah, so we've explored it a bit, but I would say that we're not using it as
So
extensively at this
just
point.
to and just to quickly add to that, I think as Vinitha said, Z ordering we have explored. One more point I remember is like the partition and the stats were much more beneficial, especially the stats for most of the type of queries. And Z ordering, because Z ordering also needs to be changed on the ingestion layer, and you need to change the table spec. So we found that the stats generation and stat generation especially is non-intrusive and can help a lot.
Great, thank you. 5 minutes, I think we can fit in one more question. So I'll go for the next one. Can you elaborate on how NDV in brackets number of distinct values, stats generation helps in improving performance, especially in complex machine learning feature engineering pipelines?
That's a good question. I think maybe we might need a little bit more time to discuss that. But I mean, again, uh, machine learning and AI related use cases, I think ultimately we have to see what kind of queries we are running. So if I know the type of queries, if it has joins, and if it has complex joins, and it is not able to identify automatically what is my left side table versus right side table, it boils down to that. If I have those kind of queries, it will help.
Okay, thank you. And this might be another lengthy one as well, but it's the top voted. So as we evaluate moving CDC-based pipelines from Snowflake to Iceberg, I'm curious, what infrastructure, platform decisions, e.g. query engines, orchestration, cloud storage, catalog type, etc., most impacted your pipeline performance and reliability? We've got 3 minutes.
Yeah, we'll get a prize for this. But if I or Vinitha, you want to take? If I understood this correctly, it is CDC. I don't get it what exactly CDC is, but I think what we are
So
trying to
change
understand is
data
change
capture.
data. Oh, okay.
Yeah, I guess if you can elaborate a little bit more on the question, like is it related to CDC, or the question is more around overall what are the decisions that impacted the performance and reliability the most? Yeah, so I think it's a little ambiguous, but if I interpret as like what are the major takeaways for us from a query engine perspective, I think to ensure that first of all we are constantly innovating in the space. Trino is not the only engine. There are other engines that we're actively exploring as well. In terms of orchestration, there are things like Airflow and other tools that are being leveraged. Cloud storage, again, here this is not like one thing fits well. There's sort of more storage agnostic architecture is something that we're sort of overall rooting for. And catalogs, as mentioned, the REST catalog is something that we're sort of doubling down on.
Perfect. Thank you so much. And at the risk of asking you a question with another really long answer, as they seem to all be so detailed, everybody's fascinated by everything you've said. Thank you so much. I think we'll wrap up the questions now. And thank you for joining us, Manish and Vinitha. As a reminder, all sessions will be available on demand within 1 hour after the event. And up next in track 4, we have Transforming Manufacturing Data, Illumina's Journey with Apache Iceberg, presented by Stephen Horn with Illumia. So see you there. Thank you so much.
Thanks a lot. Thank you.
Thank you.